Hi everybody. I'll begin today just giving a brief overview of trace minerals and then we'll move on to a discussion about iron. So what exactly are trace minerals, or what do we know about them? We need them in much smaller amounts than the other minerals. They're essential for health. They are hard to study because there's only small quantities found in the body. Animal sources are the best way to get these trace minerals, and generally trace minerals from animal sources are better absorbed. Sometimes they're called trace elements or microminerals, depending on your source or your resource that you're using. Typically defined as being needed in amounts less than 100 milligrams on a daily basis, ultra trace if less than 1 milligram per day is required. The RDAs are established for 6 of the trace minerals and AIs are established for 2 others. So let's talk about iron. There are 2 forms of iron, heme and non-heme forms. Heme iron accounts for about 60% of the iron in meat, fish, and poultry. And then the non-heme iron is mainly found in your plant foods. So when you have your breakfast cereal, cold cereal in the morning, and it says is a good source of iron, it's that non-heme iron. Food sources I've listed for you: red meats, seafood, legumes, dark leafy greens. Again, the dark leafy greens would be the non-heme source. The red meats would be the heme source. As I was mentioning, many grain foods are fortified with iron, and oral supplements come in the form of ferrous iron. And there's my iron title slide. Don't know why it was there. I was wondering where it went. Iron digestion and absorption. Heme iron is hydrolyzed from hemoglobin and myoglobin, which carries oxygen, and that happens in the stomach and small intestine. And there's a specific heme carrier protein that will help with absorption. And ultimately, it's hydrolyzed to inorganic ferrous iron and protoporphyrin. Non-heme iron has to be hydrolyzed in the GI tract, and it's reduced from... So ferric iron is reduced to ferrous iron, and that remains fairly soluble. And that ferrous iron, so the Fe2, passes into the small intestine and becomes more alkaline. The main or major transporter of iron is a divalent cation, and it's called DMT1. And synthesis of DMT1 is affected by iron status. So the body really is in tune to what your stores of certain nutrients are, and can either uptick or upregulate, I should say, or downregulate the absorption. Non-heme iron absorption is enhanced by certain things such as sugars, fructose, which occurs in fruit, and sorbitol, which is a sugar alcohol. If you eat too much of that, you're probably going to get diarrhea. So I wouldn't necessarily take in sorbitol so that you increase your non-heme iron absorption. I'd go instead with some vitamin C, so ascorbic acid. Have some orange juice with your breakfast cereal in the morning. That would be my recommendation. And non-heme iron absorption is also enhanced with the rich heme sources such as the meat, poultry, and fish. Inhibitors of non-heme iron absorption include polyphenols, so from tea, if you drink a lot of tea, oxalic acid, phytic acid from plants, and the divalent cations, calcium, zinc, and manganese. Intestinal cell iron use. So once the iron gets into the enterocyte, so in the small intestinal cell, it's either used in a functional capacity or it's stored in a ferritin form. It's actually transported across the small intestine cell's basolateral membrane, and then it will enter into circulation for transport to the various body tissues where it's needed. Ferric iron in the blood is attached to the protein transferrin, and the iron pool, plasma iron pool, contains about 3 to 4 milligrams of iron, which is in fact bound to that transferrin, that protein. Unbound iron is actually a problem. It can generate radicals, free radicals. So free iron reacts readily with hydrogen peroxide, and that is not a good thing. The half-life of transferrin is about 7 to 10 days. That's good to know if you're ordering labs, so you don't repeat the lab before a change might occur. Storage sites include the liver, the bone marrow, and the spleen. The storage proteins, in addition to ferritin, are hemosiderin, and that actually increases during iron overload because it's the body's attempt to store the iron without causing harm. I mentioned, I believe, just a few minutes ago that iron was important for hemoglobin and myoglobin for oxygen delivery to the cells. It has a role in cytochromes and other enzymes, involvement in the electron transport chain, as well as in amino acid metabolism, carnitine synthesis, and pro-collagen synthesis. So a number of important roles. I just tend to think of the role with hemoglobin and myoglobin for oxygenating the cells. Other nutrient interactions. Vitamin C, we already talked about, enhances iron absorption. Copper deficiency will result in iron deficiency anemia, interestingly enough. Zinc inhibits iron absorption if you take them together. Vitamin A has several interactions, and then lead will actually interfere with iron absorption. Interesting story. While I was a dietetic intern at a large hospital, there was a teenager who was on total parenteral nutrition because this person had sustained blunt force trauma to the abdomen and had pancreatitis as a result. We had a resident who had written the order for the TPN and had inadvertently ordered too much iron. I'm not sure why it wasn't caught by the pharmacy, but what had happened was this particular individual actually looked bronzed from the excess iron overload that they were receiving in the IV feedings from the TPN. So they actually had to chelate the iron with a nutrient, with another mineral. I'm not sure if it was zinc or not, I don't recall, but they had to chelate or bind that iron to get it out of the body so it wasn't deposited in the organs. So it was kind of a big to-do, but they caught it in time and no harm came to the particular patient. But honest to goodness, the kid had a bronze glow, looked like he'd been spray tanned. Iron excretion occurs mostly through the GI tract, to some extent blood, bile, and mucosal cells that are broken down. Skin, again, you're getting rid of those surface cells, the epidermis. You'll lose some in the urine through the kidneys, and if you bleed out or you hemorrhage, you'll lose iron, and as well as, depending on menses, iron loss occurs there as well. The RDA, recommended dietary allowance. Men, 8 milligrams across the board. Women, it varies with their stage of life that they're in or whether they're pregnant or lactating. Iron deficiency is usually seen in specific population groups. So infants and young children we worry about adolescents, they're going through rapid growth. Menstruating females and pregnant women, they monitor iron status quite closely. Deficiency progresses to iron deficiency anemia. And it doesn't just happen like, bam, you have iron deficiency anemia. There's a series of steps that occur. And treatment does require supplements. I say that, but there are some cases of, or some people with iron deficiency anemia that actually require transfusion with iron. And they actually have an iron transfusion clinic, which solely exists for the purposes of treating iron deficiency affiliated through healthcare facilities, of course. This isn't something that's done outside of a medical facility. Those at risk also, vegans, runners tend to be at risk, and women of childbearing age in general. Pica in women and children. So pica is the consumption of non-food sources. There have been cases, there used to be a show on one of the cable networks about pica, and really bizarre things. Clay, laundry detergent, which I imagine could potentially kill you, non-nutrient, non-food sources that people consume, and that can interfere with iron absorption. Signs and symptoms: paleness, brittle nails, fatigue, weakness, SOB, shortness of breath, irritability, poor temperature control, and poor growth. Toxicity: the upper level that you should consume of iron is 45 milligrams. You can get acute iron toxicity from accidental iron overload, and I do recall several cases, not sure from what point in my life, but there were unfortunately some children that got a hold of iron supplements, and it was not good. Hemochromatosis: that is a genetic condition which results in iron overload. The body can't sense the iron stores and downregulate intestinal absorption. So there's something not working right in the body due to this genetic disorder in these people. If you get iron deposits in your organs, you're going to get organ damage, and that is not a good thing. And that can go virtually undetected until damage is to the point where it interferes with that organ's normal function at the age of 50 or 60. So I don't think it's routinely screened for. They will screen for it if there's a genetic component in the family. but it's not something that's noticed, unfortunately, usually until it's too late. How do we assess iron deficiency? Well, remember I said you don't just get iron deficiency anemia, bam. It has to occur through a series of stages. So the first stage, you have diminished iron stores, and what you would do is test the plasma or serum ferritin. Second stage, now that our iron stores are diminished, the transport iron decreases and plasma ferritin diminishes, and that circulating iron begins to decrease because we don't have that transport iron available, or the transport source. The continued progression, you have the elevation or the rise, the increase in protoporphyrin. And in the final stage, we actually get the iron deficiency anemia. And that's when we typically see in the CBC, so the complete blood count. It's a lab that's drawn, it's called the CBC. And we see that the hemoglobin and hematocrit are typically depressed or altered or lowered. That concludes the iron lecture. We'll see you next time.